Hello together to our lecture in statistics. We are in the topic of methods of forecasting, and in general, we would have a time series where we want to get out something like a trend, some try to identify cycles, seasonality, and so on, because in general our data will be an aggregate of different components, and of course in the end we will have also some random component which we could not explain. And we started with different methods in order to take here our example of a data set, quarterly data, and we want to forecast for the year 2023 for the whole year, and of course also for the quarterly data. The first one was the very simple first shot, nothing else is changing compared to history, so we just repeat the last data point. And I said to you that from the efficient market hypothesis, this is actually a quite reasonable forecast in capital markets, but in general, of course, we will take also into account the other data we have for our data series. And the first one was the moving average, where we just take maybe the 3, maybe the 5 last data points. In general, we mostly take an odd number, because then we can also smooth our data series, identifying always our smoothing average with the center of our period of, let's say, 3 or 5 or 7 last data points. And this we had done. Didn't I put in the I thought, oh, this was the last time. Then let's look at my Excel file. Forecasting. There we had our data series. Let's put it in that you can see it like this. And oh no, this was this one, where we had the moving average, that we saw that we can smooth our data, so we get rid of this seasonality effect here. And then we went on with the method of exponential smoothing. And what do we do by exponential smoothing? There we generate forecasted data x, y hat for every data point in history, and then we take the last explicit data point yt, and we calculate then a weighted average of these two values the forecasted data point and the explicit data point, and this weighted average then should be our forecasted data point for time t+1. And there actually we also directly see that we incorporate also the naive prognosis, that or the naive forecast if we take alpha equals 1, because then of course we would take as the forecasted value the value of the last data point. And I also explained to you why do we call this method exponential smoothing, and the reason is that if we start to iterate this definition of exponential smoothing, so we start to insert then for here, for this data point, the former forecasted value, and iterating this backwards until the starting point of our data series. And for the starting point, we just defined that for the started forecasted value, we take the value itself. We obtain here our factors 1 minus alpha up to 1 minus alpha to the exponent t minus 1, and that this is nothing else than the geometric series. And for geometric series, we know that the geometric series is just the discrete way to describe growth processes, and in general growth processes are described via the exponential function, and therefore we call this method exponential smoothing. And then going to our data set, we also here started to create our exponential smoothing with alpha equals 0.3 and alpha equals 0.8. And this of course means the higher we use the alpha to be in the neighborhood of 1, the more we focus on the latest data. And I think also 0.8 we already did. Let me look inside. Moving average and equals 7. No, only alpha equals 0.3. So here we already saw the diagram of the smoothing with alpha equals 3, the orange line. Okay, and then of course we also want to create our smoothing with alpha 0.8. 0.3 and 0.8. And doing this, if we have done this already in X, okay. Question, did we talk about GDP? Yes, I did recalculation of the GDP deflator, and therefore when you did you had a look in the video, because I redid this. There was a mistake in the calculation. You're totally right. And if you look at the new video, then now hopefully everything is okay. But if you still find something, then please give me a feedback. Okay. And then let's go back to the exponential smoothing with 0.8. And if we already had done this in Excel, then again, of course, we have to start with the first data point. Let's go again in our definition. So here, oops, the first data point should be the data point itself. So we can copy this. And the next data point is then the new data point, 345 times our weight now alpha, 0.8, plus our forecasted value, 1 minus 0.8, then times 330. So we can then use this formula. And now we have to change it to 0.8 and 0.8. And of course, if we take an average of the same two numbers, this has to be the number itself. But then if we go further, because of the iteration process, we obtain new forecasted values differing from the data itself. So copying this downwards and oops, this one. We obtain our new data series and the forecasted value we obtain, moving our formula one step further. And for this, if we insert this in the diagram, what would you think? How does the new line looks like? Is it closer to the orange line or closer to the blue line? What do you think? You're comparing 0.3 and 0.8. By knowing that a higher alpha means that the weight of the recent explicit data point becomes more important. What do you think? So will the line now be quite close to the orange line, or will it move in the neighborhood of the blue line? And this you should also keep in mind doing statistics. Yes, of course, closer to the blue line, because now the explicit value of our data becomes more important. The weight here of the 390, 354, 345, and so on. So we move 80% of this value we take in our forecast, and therefore we should be quite close to the line itself. Sorry, but I need here the beamer, and since nobody is inside, then every 20 minutes I have to step up, because otherwise I don't see what you see. So 80% of the data itself is taken into the average of our forecast. And this I also recommend doing statistics, that you not only take your data, putting the data into your software package, pressing enter, and well, there's something coming out. So again, I don't know. We still have technical problems. I don't know. So that doing statistics, that you also always try to have an idea what will be the result of my calculations. And so hopefully we are right if we taking this data into our diagram 0.8. $503, and as we see it here now, we did not smooth in the way as we did it with an parameter alpha equals 0.3, but we again also see the seasonality within our forecast. And as I mentioned already, it is quite complicated to use the right, so to speak, smoothing parameter alpha, and therefore it is quite important that you know how sensitive your forecast reacts by changing your weight alpha, and therefore you should know that if you have a high alpha, then you more or less repeat your explicit data, and that you use more smooth data if you use a low value of alpha. So what else should we do? At first, what kind of series would we obtain if we use alpha equals 0? as I said, then we should have a very large smoothing. And if you look in the definition, what happens if we use alpha equals 0? Let's have a look in the definition of exponential smoothing. Now alpha equals 0. How does the forecasted data look like? Well, taking alpha equals 0, then we have y hat t plus 1 equals again alpha yt plus 1 minus alpha y hat t, and now alpha equals 0. Then we obtain 1 times y hat t. And we know y hat 0 equals y 0. Then you see we just stay at our first data point. So staying at the first data point then means all our y hat t equal yt, and then of course also this will be with this, then all our y hat would be y0, and also of course explicitly y hat t plus 1 will be y0. So then we have the different extreme. Using alpha equals 1 just means we taking the naive forecast, we taking as our forecasted value the last data point, and using alpha equals 0 just means a total smoothing, so to speak. We just stay at the first data point. Okay, and let's put this also in here, and that you really see this. We again just copying our values, and now using 0 and here 0 means we definitely stay during all times at 330. Oops, these are not only numbers. So what did we do here? B5 times C5. Oh, sorry. So I have to use here the value of not C but E3. And staying at 330. Maybe here it is also wrong. It's not C. This has to be D. but this should not change that much. Yeah. Okay, and then we stay at 330 and adding this also in our series. We stay here. And in quotation marks, smoothing this alpha equals 0. Okay, what else? Calculate the revenues per year and redo the exponential smoothing with yearly data. What do we have to do then? Well, at first, this was exponential smoothing. Let's copy this one. And we want to do it with yearly data. So first of all, how do we obtain the yearly revenues? Well, just adding up all revenues, so sum. And then going down to our time series. This we can sort out. And then yeah. Now we do not have that much data points, so let's start with copying all our values. Up. And this is then 2018 up to 2022. So again, smoothing with alpha equals 0 would be then the data point itself is my first forecast, and then alpha 0.3 times our value in time t 1482 plus 1 minus 0.3 times my forecasted value. This has to be a bracket. Moving this formula downwards, we obtain our forecasted time series. And for 0.8, doing the same. And now changing the 0.3 with the 0.8. And now we have to also, of course, change this F and G. And again, and for alpha equals 0, this one. And now we already know that we are staying at the first data point. So just copying this, moving downwards, and we obtain our time series with alpha equals 0. So now plotting all our data, here we could say data. Let's see how it looks like in this case. And manipulating also our vertical axis. Let's say from 1000 to 2100, or we start at 1300 and let's end up at 2100. Okay. Then again, we see that with alpha equals 0.8, we are much closer at the original data. And sorry, I forgot, of course, we want also to forecast, of course, 2023. Just moving this one. And what did I wrong? Two 2023. Again, something is wrong. We want to have, oh, sorry, there I switched again. In here, this has to be, of course, E3, because it is the sum of the data, the forecasted data point is the data point itself, 1419, plus the weighted forecasted data. Again, you see, you should always have an idea what you are doing, because then you directly see when you are doing something wrong. A bit closer that you see all the diagram. No. Oops. Like this. And then we have also the forecasted, and we can just move this downward in order to obtain the forecasted value here for the year 2023. Okay, so this is our example with exponential smoothing. And in order to summarize this, this we quite often take if we do not have a clear trend in our data, then this method is quite often used, because otherwise, of course, and this we will do in our next exercise, then we at first would try to identify this trend, and maybe then we can do also stepwise. At first we identifying a trend, and with the rest of our data taking out the trend or component, then we, for example, could use the smoothing, the exponential smoothing, to have an idea how the rest of the data without our trend is developing over time. Also, we use it maybe for a first shot, explicitly for very short forecasts, and as I said, it is not an easy task to identify a good, so to speak, alpha. But if we compare this with some classical just averaging our data with this exponential smoothing, we have, so to speak, a parameter, and with this parameter we can play and we can look, is it better to incorporate with a higher weight the data of the last explicit data points, or should I do a more general smoothing? This is then always a task for the good forecasters. So then we will go to average, the method of average growth rate. I think you already have seen this method. We actually also have done this when we, for example, calculate average growth rate of an economy or something like this. Also averaging growth rates using the average inflation rate or something is nothing else. So this is also then maybe something that we say, let's try to identify a general trend, and that you have maybe a bit careful with averaging growth rates. For this, I brought you a very simple example, because quite often, in order to calculating average growth rates, we just take the arithmetic mean, and that this is actually not right. We can have a look at this example here. So let's take development of two stocks. Stock price A and stock price B should evolve over time, as in our example, from 5 to 10 to 10 for stock price 8, and from 5 to 7.5 to 11.25 for stock price B. So what is the growth rate in 2020 for stock price 8A? So I want to calculate this cell here. What do I have to do? if you have a jump of a stock price from 5 to 10. Then we have an increase of how much percentage. So everybody is maybe drinking a cup of coffee, and then this one would be nothing else than 10 minus 5 over 5 is of course 100%. And the next one, 10 to 10, is of course nothing, so 0%. From 5 to 7.5, over 5 is of course 50%, and 11.25 minus 7.5 over 7.5 is of course also 50%. Taking the average arithmetic mean in this case would be 100% plus 0% over 2 is 50%. And averaging here is 50% plus 50% over 2 would be also 50%. But of course 10 is not equal to 11.25, and therefore this is actually wrong. So what do we have to do then in order to calculate the right average growth rate? This just means that we more or less make the thought experiment that we have our starting data point y0 and our last data point in t equals n, yn, and then we ask for the growth rate constant over time, so that we then have to calculate y0 equals 1 plus g times 1 plus g times 1 plus g times 1 plus g, and this n times equals our last data point. And solving this for g then means yn over y0 equals 1 plus g up to n. Taking the nth root means nth root over yn over 0. This we also can write as yn over y0, 1 over n equals 1 plus g. And then, of course, we obtain g equals yn over y0 up to 1 over n minus 1. And this here we can rewrite as the product of the series of all relative values, so the proportions of time t over time t minus 1. And then of course we see here that all these cancels out, and we end up with yn over y0, and this means that we have to calculate the geometric mean of our growth factors. And then, after having calculated our averaged growth rate, we take this growth rate and add this to our last data point, assuming now that we are growing with the same growth rate in the future. So we obtain the next data point by multiplying 1 plus the growth rate, though this is then also our averaged growth factor. And of course, we can go further on into the future using k times this growth factor. We then obtain the forecasted value in t plus k. Well, then let's use this method in order to calculate the year 2023 for our data set. And in B, we at first want to use the trended data that we are using the average quarterly growth rate from starting in 2018 Q1. And this we also want to redo with our aggregated data per year. So then let's start forecasting. Let's copy this one. Average growth. This we do not need, and this is the yearly data. First, we want to obtain our average growth rate over the whole time series. So how many data points do we have? Let's count them. 1, 0 equals this plus 1 downwards. So here we calculate our growth factors. This is nothing else than 345 over 330. moving this down to the end of our data series, and then our average growth factor. Let's put in some more lines. So average growth factor is then the geometric mean of our total growth factors and averaged growth rate is then our growth factor minus 1. Let's do this in percentage. And our forecasted values are then taking this growth rate or growth factor for using starting at 510, our last data point. So this one, 510 times our growth factor. This one we have to fix. And let's put this one here. This is then our forecasted data. So then let's take this out, and this is our revenue, and let's see how it looks like. And this we take out. And now this would mean that this is our data itself, and here we have then our forecast, and actually we also see that of course we have no seasonality anymore in this data, since we just apply a constant growth rate. So with this quarterly data, we also can of course then use this forecasted data here in order to make a forecast for the whole revenue of 2023, and this means just we sum up this data, and then this number here would be our forecast from quarterly data. Then we would have 2023 161. But of course, we can also do a forecast of 2023 in another way, that we just use directly the total revenues of every year. And then, of course, we again have to calculate the growth factors. This would be, again, the proportions of the value itself divided by the former value. Take more digits. And then again, we calculate again the average growth factor and the average growth rate by taking the geometric mean of our growth factors, and the average growth rate would be then growth factor minus 1. So in this case we have 8.6%, and also we can then use this average growth factor for a forecast from yearly data. So this would be then quarterly data or yearly data. And for this, we then have to calculate our yearly number, 1974 times the average growth factor calculated from yearly data. And then we see, of course, that we obtain another value compared to the value from the quarterly data. And what we see here is that the 2161 is larger than 2144, and this comes more or less from the fact that looking at our data, we have here, due to the seasonality, very high jumps in the data, and with this also that if we look at the cycle, that we end up here in the end of our data set not with a low value due to seasonality, but with the second highest value. So in general, this means that we then take high values by calculating on the quarterly basis more often than the lower values. And due to this, we end up with the fact that we have here a higher forecast for the annual data using quarterly data or using yearly data. But actually, we cannot say which method is better. Also, again here, the good forecaster has to decide what to do. And for a last, let's also summarize all this. So in general, the average method is actually always used when we see a clear trend. And so in our case, it is quite a good method because we see that Um, taking the seasonality out of our data, then we see that we have this clear growing trend in our data. And also this is one of the first estimation or the first shot we do quite often. Again, a quite good property of this method is that if we have a quite long time series, then this more or less ignores if you have an outlier within your time series in the middle, because actually we are using only the last and the first data point in order to calculate the average growth rate. But on the other side, we are then quite sensitive for the last and the first data point. And this actually we already have seen here, because using quarterly data means that we give a very high that we take this high last data point as the very important data point in comparing this one with this low data point due to the seasonality of our data. And so I talked quite much about seasonality, and therefore I want to show you one possibility to incorporate this seasonality effect in our forecasting process in order to get data for the year 2023. And this actually can be done quite easily in a descriptive way. That again, we start calculating the yearly data, which we have already done. And then we calculating the average proportion of every quarter due to our yearly data. And then we use some method, maybe average growth rate, exponential growth, smoothing, in order to get a forecast for the whole year of 2023. And then we use the averaged proportions for the seasonality of the year 2023. So let's do this also. Again, we are copying our data. And now what we need is always the quarters. And now we sum up again the total revenue. Yep. But what we want to have now is, yeah, let's put this always one to the right. Yeah, you still see this, and 2018 we need also. We need also the sum of 2018. And now we calculate just the proportion of every quarter. So 330 divided by 1490. And this we do always for all 3 quarters. But first we have 23%, 24, 27, and 25. And also here, let's move this one to the right, because then we can copy this one just in here, in here, in here, and in here. A bit closer. But what we want to have now is, let's also use here percentage. Oop. That we now want to calculate the average proportions. And this would be then 23 plus 23 plus 23 plus 22 over 4. And of course, I need here some brackets. And this would be then our average proportions. And with these proportions, we go into our forecast. And we had here our yearly forecast from exponential smoothing with alpha equals 0.3 and alpha equals 0.8. So let's take these two values here. So this is 23. Oops. Not format. This was exponential smoothing with 0.3. And exponential smoothing with 0.8, I think. Did I copy it in the right way? This is 0.3 and this is 0.8. This should be H3, H3, H3. And let's also take the average growth rate. And there, let's take this one from yearly data. Average growth rate yearly data. And this was 2144. Oops. 2144. And now we can say then that using these averages here, for example, using this average growth rate of 2144, we obtain then 2018 exchanging 2023. That we use 2144 times the average proportion. This we have to fix again. And then we can use this as the forecasted values on quarterly basis. So let's add this one now here at our series. And plot this now. And adding the series of our forecast. Would be then forecast we need, oh sorry, at first we have to move all this data here one to the right in order to show you the diagram. So that would be then the forecast, and now we can edit by taking this and this one and using this as the forecast. So this would be then our forecast I think the legend is here. And then you see that we more or less can repeat our seasonally pattern with this method by averaging just the proportions of the four years from 2018 to 2022. Okay, with this we are done with our forecast methods, and the next time we will start with the second exercise, which I uploaded you already. So then, thank you very much for today.